Hello, this is section 9.2, which is on vectors. And some of the things that we're going to look at in this particular section is how to add vectors, how to multiply by a scalar. We'll look at different components of the vectors, length, both two-dimensional and three-dimensional. We'll look at the different properties of vectors, we'll talk about unit vectors, and then our standard basis vectors I, J, and K. And so for some of you, this is material that you have seen a little bit more recently, and it might be a little bit easier, which is okay. And for others of you, this is going to be relatively brand new, and so I'll try to kind of go over all the different aspects of this and not go too quickly through anything. So first off, we have a vector, and I always think of, I think it's Despicable Me or one of those movies that I've watched with my kids, where they talk about that a vector has both magnitude and direction. There's that scene that I'm imagining now with the piranha gun or something like that. But anyway, you may know what I'm talking about, or you may think I'm a little crazy. I don't know. But with a vector, we have both magnitude, which is the length of it. I'll talk about that actually probably in the second video for this section. In addition to the direction itself. And so when we look at a particular vector, the point here would be considered the initial point, and this point here where sort of that vector ends, that's going to be the terminal point. And so we have these different vectors that we can look at the magnitude and direction of them, and I'll talk about placement in a little bit. In terms of notation, you might have seen, depending on which class you've come from, whether it's AP or IB, you'll see different types of notation. What I'll often do is I'll write my vector notation like this. This would be vector V. Vector V may be made up of, let's say, 1 for the component in the x direction and 3 for the component in the y direction. And so you'll see that as well. If you're coming from AP, we really do very little with vectors. We do a little bit with a velocity vector, a little bit with acceleration vector, and you've seen that notation in AP. I know that with some other classes, I know some of the IB classes, some of the honors pre-calc classes, they'll use almost more of a bracket notation or a parenthesis notation like this. Oops, sorry, not divide. And so, I'm comfortable reading all of that. So if you have a certain method that you're more used to, you can certainly use that. You'll see across the nation at different colleges and universities, they use different methods depending on the professor, depending on the school. One big thing that I want to make sure that you all do is that when you're writing a vector, I don't want you to write it like an ordered pair, because I think that's very confusing. And while you actually see that a little bit in some textbooks and in some college courses, I really would like you to use more of a traditional vector notation so that we know that it's a vector, not a point. Okay? With equivalent vectors, what this means is that if you have vector A and it's equivalent to vector B, it has the same length and direction, but it could have a different position. So for instance, if you had on a plane here, let's just talk about two dimensions. So if you had a vector, let's say A was here, okay, and B was maybe here, and just pretend like I'm doing this perfectly. So what I'm talking about here is that they have different positions on the plane, yet they have the same length and the same direction. So those would be considered equivalent vectors, and you obviously could have a huge number of equivalent vectors. Okay, in terms of combining vectors, so when we're looking at combining vectors, so for instance, let's look at AB. So if you took a look at the vector AB and we add it to the vector BC, one of the easiest ways to do this is to take vector AB, the terminal point of vector AB, we would then start the vector BC, and then the resultant vector would be AC. So this is something that I believe pretty much all of you have had in honors pre-calculus, but this is just the definition of addition of vectors. Now, with this, we have the triangle law and the parallelogram law, and again, you might have seen these before, maybe not. I don't know. But what you're doing here with triangular law is that you're just kind of what I just said, you're going to start with the initial point, go to the terminal point of one vector, and then that starts the next vector's initial point to the terminal, and you end up with the resultant sum of those vectors. Now, if you look at the parallelogram law, you can see that you can sort of do this in two different ways, and the way that that happens is that we have a commutative property of addition. So we could take u plus v, and it's the same thing as v plus u. All right, let's go to the next page now. And this page, what we're going to talk about just in this first example is doing the sum of these types of vectors, okay? So let's take, for instance, let's take a look at vector A, and I'll give it my best sketch here. So let's say vector A looks like this. And if we take that and then add B to it, then we get the resultant vector between those right here. We could call that C, let's say. Or what we could do is we could take B, let's say that that's B, and we have A then. I'll redraw that just for a second here. So there's, let's say that's A. And so then what we get is C. And you can, I mean, again, my sketch is a little bit off here, but you can see that no matter the approach we take, the A vector and then the B vector, or the B vector and then the A vector, as long as we have the correct length and direction, we're going to get the same resultant vector. So that vector C is the same in both cases. All right, let's talk a little bit about negative vectors. So if you have a vector, let's say it's negative A, okay? That really what that is -1 times what vector A is. So this is kind of like a scalar, which I'll talk about in a minute. But negative vectors just mean that if you started with a vector A, let's say, and you're comparing it to vector -A, that means that the length is exactly the same, but now the direction has changed. You've multiplied by a scalar in order to change the direction of that particular vector. And you can see that with differences of vectors, when we were to subtract them, really what we're doing is we're taking u and we're adding -1 times v. That's sort of the mathematical conclusion there, is that we have u plus -1, so the scaled vector v. And you can see in the drawing here that v is now being multiplied by -1, so therefore it's going to go in this direction, and then we're going to add u to it, and we get u minus v, or here's another one here. Let's try that. So let's move this down. Oh, sorry, let's talk about this first really quick. So what I was just explaining there in terms of the negative vector is that there's the scalar to that. We're multiplying by -1. Well, we can multiply by all sorts of different things. So for instance, we could multiply v by 2, and therefore it's the same exact direction, but now it's twice as long. So we've changed the length, or 1/2, changed the length. The negative here, that would be changing the direction. So let's try example 2, and we're given a little picture for A and B, and we're going to sketch A minus 2B. So let's start with A. So A looks like this, and then B would, obviously be something like that. However, what we're going to do is we're going to do -2B. So we're going to make B go in the other direction, and it's going to be twice as long, like that. So that's going to be -2B, and so then our resultant vector here will be A minus 2B. Okay, let's go on to our next page. All right, in this little piece, we're going to talk about the components of vectors, and we're going to look at both 2-dimensional and 3-dimensional vectors. So obviously with 2-dimensional vectors, you're going to have a component that represents the amount you've moved in the x direction, and then the second component will be the amount in the y direction. So this little bit right here would be a sub 1, and then this would be a sub 2. And then of course with 3 components, now we just have that added z. And so let me just draw this out for you. So let's say that this is approximately excuse me, a sub 1, and then this would be approximately a sub 2, and then we have the z component, which is a sub 3. So really the reason that we have these vectors, the reason we have these components is to find a point in space, whether it's in a plane or in space, but we want to be able to find it quickly and accurately, and so vectors allow us to do that. Again, it's really important that we write this as a vector versus a point, because you can, write it as a point and it becomes very confusing. Now, here's the part that I think that sometimes we get a little bit thrown off by, and that is that if you notice the point a sub 1, a sub 2 exists at the terminal side of the vector a that we just defined. Now, vector a happens to have the same components as the ordered pair. The reason for that is that vector a, the way that it's drawn in this picture right here, is called a position vector. And a position vector is defined below. It's a vector that has its initial point at the origin. So what happens with position vectors is that they start at the origin and their terminal point is an ordered pair that looks almost identical to the vector components itself. The only difference is how it's written. So for instance, if we take a look at this particular vector right here, notice that the terminal point is 3, 2. Well, the vector is also 3, 2, but it's because it's a position vector. What if we had the exact same direction and magnitude, and we were to look at this particular vector right here? This vector is still 3, 2, because again, it's magnitude and direction. However, the terminal point right here is not 3, 2. The initial point is not 3, 2, and is not the origin. So it can become a little bit confusing because these vectors can be sort of plucked out of a plane or space, and they can be moved into a different area for the purpose that we need them to be. And it's really important to know that the components of the vector don't dictate where it is in that plane or in space. If we are given two different points, then we're able to find the vector between them. And it's a very simple calculation. All you're going to do is take the terminal point, the x component of that, and subtract it from the x component of the initial point, then the y of the terminal minus the y of the initial, and so on. And you can do this with either 3 or 2 dimensions. I'm going to model this in example 3. So in example 3, we're going to find a vector that represents the direction by the directed line segment with the initial point. So we have B as our terminal point. So we take the vector AB and we get, I'm going to write it all out just so that you see it. I know that you guys can do this, but we're going to take -2 and we'll subtract the first component of A, which is 2. Then we take the component of B, which is 1, and we subtract the middle component of A, which is -3. And then we have 1 from B minus 4 from A, and that gives us our third component there. And then obviously you'd want to simplify this down to find our final answer. This is probably the only time you would ever even consider writing that out in full. You all will do this in your head because it's so easy to do. But remember, I mentioned this in the other video as well, that even the most trivial things in this class at the beginning, they become difficult all of a sudden when you're starting to do a crazy calculation. So just keep in mind, don't overlook the simple stuff, okay? You all need to be able to find the vector that's represented between 2 points. Okay, we're going to stop there on this video. The next video will cover the remaining, or at least the other pieces to this particular section.